All right, good morning, chemists. We'll get started and jump right back into thermochemistry and calorimetry. This is a very calculator-based section, so might as well have those calculators out now. So we left off on this slide, just about to jump into those calorimetry calculations. These calculations you will use extensively in your IHT lab, which comes up, I think, after fall break. So this was our last full week. Next week we will be rewarded with a short week. We just have lecture on Tuesday, and then back to full weeks. So yeah, IHT doesn't come until after fall break, but the calculations we're going to go over today. All right. So the idea of calorimetry is that we are doing a chemical reaction or observing some type of process inside a coffee cup. This is called coffee cup calorimetry. The big idea is that there is water inside this cup, and we use a thermometer to track the temperature changes of the water. So what you really need to get behind is that when you have your thermometer measuring the water in the cup, you are actually measuring the surroundings. The chemical reaction, that is your system. That's what we care about. So when we see the temperature increase of our thermometer, that's because our reaction released energy. That is an exothermic reaction. Delta H is negative. So use your intuition there. Or on the other hand, if the temperature of the thermometer decreases, goes down, it's because the reaction absorbed energy. It stole energy from the surrounding water, resulting in a temperature decrease. That is an endothermic reaction. This reaction requires energy to get started. So delta H of your reaction is a positive value. I promise you, you are going to screw up on these signs, but make the mistake now so you don't make the mistake on the exam. So with calorimetry, really what we're doing is utilizing the first law of thermodynamics, which is right here. The heat lost somewhere is always the heat gained somewhere else. So we're just going to be clever and say, okay, the reaction is losing heat, therefore the surroundings, the water is gaining that heat. So typically what we're doing is measuring the surroundings, and we relate it back to the actual reaction, the actual system. So how we measure the surroundings is with the equations we talked about in prior sections, where we're going to use Q equals MCAT or Q equals CAT, depending on what that system is. So let's jump into it and see if we can't use our intuition. First, get the sign of the process correct, and then calculate it numerically. All right, so here's our first example. You will do this in your I think so, in your IHT lab, so let's see. All right, so we're going to take a 6.5 gram sample of sodium hydroxide, and we're going to dissolve it in 100 grams of water, all right? And we're going to do this all inside that coffee calorimetry cup. And so when we do this, what we observe is that the entire solution temperature rises from 21.6 degrees Celsius to 27 degrees Celsius. I tell you that the specific heat of the solution is the same as water. Let's calculate the delta H of the reaction in kilojoules per mole for this process. So the reaction that's happening is that we're just dissolving sodium hydroxide, all right? And we want to figure out what is the delta H for this reaction. So essentially, we are calculating or determining the full thermochemical equation for this process. So we have all the information, that we need to answer this question, and it's very systematic. Whenever I'm given thermochemistry or calorimetry questions, I always start with using my intuition and determining that sign of this process. Think about what happens. We throw the salt into water to dissolve it. The solution heats up. Is this an exothermic process or an endothermic process? What do we think? Exo. So delta H is what sign? Negative. So keep that in the back of your mind, because you're going to do all these calculations, and you better make sure that the delta H that you calculate at the end is a negative sign, so it matches our observations. So yes, this process is exothermic because the solution gets hot. We should expect delta H to be negative. So let's make sure it is at the end. All right, next we have to calculate Q involved with this reaction. So we are going to utilize that first law of thermodynamics. So the heat lost by something is always gained by something else. So we can be super specific and say, oh, this reaction lost energy and it was gained by the surroundings. In this case, it is the water. And I think I have that all over here as well, or I guess not the water, I want to say the solution. All right, so all of these Q equations, they mean the same thing. It's just different ways of thinking it, you know, defining what is your system, what is your surroundings. In this case, the reaction is the system, the solution is the surroundings. All right, so our reaction, we want to figure out how much heat is involved in this reaction. That thermometer is not measuring the reaction directly. Instead, it's measuring the changes in temperature of the solution. So what we're going to do is Q equals MCAT to the solution, because let's think about it. That thermometer is in the solution. We know its temperature change. So we know it's delta T, right? Do we know the mass of the solution? Do we know how much matter is inside that cup? Yes, we do. And then do we know the specific heat of that solution? Yes, we do, because it's the same as water. So what I'm going to do is say Q of the reaction, because we can't measure that directly, is equal to the Q of the solution, which is mass of your solution, specific heat of the solution, and delta T of your solution. These are all things that were given to us in the question, all the information about the solution. But now we got to be careful. All right, so what is the mass of our solution? What is everything that's the mass of everything inside that cup? Think about what's in that cup. Water is in the cup, but what else is in the cup? The salt. So what a lot of students will do is say, oh, the mass of the solution is 100 grams because there's 100 grams of water. But is that true? It is not. It is actually 106.5. So you want to use the entire mass of everything in that cup, which includes water and that salt. So mass of your solution is actually 106.5. It's everything in that cup. All right? Specific heat of the solution, we know what that is. It's going to be the same as water because this solution is, the majority of it is water, so it'll behave like water. And then the last one here is delta T. That information is given here, the change in temperature. It is always final minus initial. So delta T is equal to 37.8 minus 21.6. And that is equal to, I wrote it somewhere, did I write it somewhere? 16.2 degrees Celsius, all right? So these are the numbers that we are going to plug in into this equation. So let's rewrite this. Negative Q of our reaction is equal to mass of the solution, so 106.5 grams. Specific heat of the solution, which is the same as water, 4.184 joule, gram, degree Celsius. And then finally, delta T, how much this solution changed temperature. So it increased 16.2 degrees Celsius. And so when you cancel units, you see, okay, grams cancels, Celsius cancels. So we do get that Q reaction ends up being a joule amount, so an energy amount, which is good. All right, so negative Q reaction equals, what is this? Positive 7219 joules, I think. All right, so about 7,000 joules. What this number means is that the solution gained this amount of energy to heat itself up. All right, the temperature of the solution went up because it gained 7,000 joules of energy. But notice we just calculated negative Q of the reaction. So if the solution gained that amount of energy, that means the reaction lost that amount of energy. So we have to do one more step and actually get, oh, the positive Q of the reaction is negative 7,219 joules. All right? So that's not quite our answer yet. What this number means is that the reaction lost 7,000 joules of energy. It was gained by the solution, thus heating it up, all right? But this amount of energy is how much energy was released by reacting 6.5 grams of salt. If I did the reaction with, let's say, 10 grams of sodium hydroxide, would we get that same Q value? No, and it's because enthalpy is an extensive process. So this number is very meaningless to scientists who want to compare data. Let's say you do this experiment and calculate this Q. Your lab mate does a similar experiment, but with a slightly different amount of salt, gets a different Q. So let's calculate a quantity so we can compare them, and that is calculating delta H. And that's what the final question, what it actually asks us to do, is calculate delta H of this reaction in kilojoules per mole. So what we're going to do is take this Q we just calculated and scale it to a mole amount. This is how much energy is released when reacting 6.5. So let's figure out how much energy is released when we react a whole mole's worth of this substance. So to do that, we're going to use this last equation right here. Delta H of reaction is equal to the Q of the reaction over the mole amount we actually reacted. This is what will scale it into a kilojoule per mole unit of what we want. So we're going to take this number, calculate delta H of the reaction. I'm going to go ahead and convert this to kilojoules. So this is negative 7.219 kilojoules for this reaction. But this reaction only reacted 6.5 grams of sodium hydroxide. So together with sodium hydroxide's molar mass, which is 40 grams per mole, we can convert that number into a mole amount. So I'll just do that in one step here. So 6.5 grams times, I guess we're going to divide by its molar mass, so 40 grams is 1 mole. So this whole denominator, I think, is equal to 0.1625 moles. So what I'm going to do is divide the kilojoule amount that this reaction actually reacted, divide by the mole amount that's actually there, and we should get a value, it's right there, negative 44.4 kilojoules per mole. So all we did is divide that by the mole amount that's actually reacted to convert this into a kilojoule per mole amount, so we can make the comparison with, you know, any other chemist who does this same reaction with slightly different masses, right? And so this negative 44.4 kilojoule amount, this is like a number, a quantity you could look up in a textbook if you look up the heat of dissolution for this substance, and hopefully your experimental value is close to that literature value that you find online. All right, so that's one example of using calorimetry. In this case, we dissolved a salt. The temperature of the water went up. So this is an exothermic process. Oh, we didn't check our work. Is the sign of our answer correct? Yes, it is. So it's a negative delta H. It's an exothermic process that matches our observation for what happened in this reaction. The temperature of the solution went up, all right? Okay, so let's do, actually before I move on, there's a lot of steps in this question, and it's, there's a lot of places that you can go wrong, and if you are to be wrong, what is the most common mistake that students will make, probably? The sign, right? So here's a story. It's a self-deprecating story. So I've been teaching here for, I don't know, like 4 or 5 years. And when I first started teaching, my first year, you know, someone else, since we do common exams, someone else or like a group of lecturers would write each of the exams. And so when this chapter came up and they released the exam to us instructors to check, I would always try to do the exams when we received them for the first time. I'd try to do it as fast as possible, just to see if I still had it, you know, if I could still do it. So I did this exam in 7 minutes. All right, so it was chapters 4, 5, and 6. So I did it in 7 minutes. It was 30 questions. But I got one question wrong. Which one did I get wrong? I got this one wrong. And why did I get it wrong? It was the sign. Yeah, I was kicking myself. So that's why I always tell this story, you know. We can be really, really good at putting in numbers in our calculator, right? But it was the sign that messed me up at the end, all right? That I just didn't check my sign, all right? So, okay, so let's do another one, a little bit different. Okay, so here a student mixes 50 milliliters of HCl and 50 milliliters of sodium hydroxide in a coffee cup. The temperature of the solution increases from that to that. Calculate the enthalpy change for this reaction in kilojoules per mole again. So we are doing a different reaction. This time it's a neutralization reaction, but the concept is still the same. All right, the first thing you should ask yourself is, based upon the temperature change, what should our sign of delta H be at the very end? It should be what, positive or negative? Negative, yes, because the temperature of the solution went up because the reaction lost energy for it to heat up that solution, all right? So we can see that this temperature change is about 6.5 degrees. All right, this question, we will approach it the exact same as the previous one. The heat lost by something is always gained by something else. That's the first law of thermodynamics. So we're going to say, because we're chemists, that the negative Q of the reaction is equal to the positive Q of the solution, right? We can't measure the reaction directly, but we can measure stuff about the solution using Q equals MCAT. So I'm going to rewrite this as negative Q of our reaction is mass of my solution, specific heat of my solution, and then delta T of my solution. So let's see if we don't already know or have the information of those variables. Do we know the mass of the solution? What is the mass of everything in that cup? What do you think? What's in that cup? 50 milliliters of this, 50 milliliters of that. If you look at the rest of the question, I tell you just assume the density of the solution is 1 gram per milliliter. So can you tell me the mass of this solution? It's just going to be 100 grams, yes. Okay, 100 grams. Right? Specific heat of the solution, it's going to be the same as water, so it's 4.184. So this looks very familiar as the previous one. And then delta T, final minus initial. So it's going to be, I can do that in my head, right? 6.5 degrees Celsius, positive, okay, because the solution went up. All right, so those are all the terms that we need to place in that Q equals MCAT equation. So negative Q of our reaction is equal to 100 grams, specific heat 4.184, and then delta T 6.5. All right, so we just calculated that the solution gained how much heat? How much heat? Let's see, 2,719 joules, right? That's how much heat our solution gained via its mass, its specific heat, and its temperature change. That heat came from where? The reaction. So this number is equal to negative Q of the reaction. The solution gained the heat, so therefore the reaction lost this amount of heat. So Q of reaction is equal to negative 2,719 joules. And so this is the step I forgot to do when I did the exam in 7 minutes, right? Okay, but is this our answer? Is this enthalpy of the reaction? No, this is the heat involved in just this reaction, this specific one where we mix together, you know, some random amounts of stuff. We want to scale this up into a kilojoule per mole amount that we can like look up in a table. So what we're going to do is utilize the delta H of reaction equation, which is Q of the reaction. So how much heat was involved in this reaction, and we're going to divide it by the mole amount that we actually reacted. So look back at the question. It says to calculate this neutralization reaction in kilojoules per mole of HCl. So specifically, we already have the top number. We want to figure out how many moles of HCl are present here, and that's what we're going to divide by. So this quantity will be negative. I'm going to convert this into kilojoules, so 2.719 kilojoules over, let's calculate how many moles of HCl reacted. So we got to look back at the question that's given. What are we mixing together? 50 milliliters of 1 molarity HCl, 50 milliliters of 1 molarity sodium hydroxide. So we can take the volume and concentration of HCl and determine how many moles are there. So what this denominator is 0.05 liters of HCl multiplied by its molarity. So 1 liter, 1 mole of HCl, that's its molarity. So this whole denominator is 0.05 moles of HCl is present. All right, so what we see is that reacting 0.05 moles of HCl only releases 2.7 kilojoules of energy. So scaling this up to like a whole mole amount, we get this value. If you divide those two numbers there, that reacting a mole's worth of HCl will release 54 kilojoules of energy per mole of reaction that you actually react. Right, so this question, I hope you see it's very similar to the previous one, all right? Use the information in your observations to calculate Q of your reaction and divide by the mole amount that you actually reacted to get our enthalpy quantity. All right, so cool. All right, let's do another one, but this one's slightly different because it's not really a reaction, but we can still use the same coffee cup process to approach this question. So in this one, system and surroundings, again, isn't a reaction. It's not as obvious, but just think about how heat is being transferred. So what are we doing? We're taking a hot 35-gram aluminum cube at 95 degrees Celsius, and we're placing it in 100 grams of water. That is initially 19 degrees Celsius. All right, what is the final temperature of the water when the metal cube and the water become equal, right? So this is a little bit different because a reaction isn't happening, but we can still use the first law of thermodynamics to approach this. So what's happening? This is basically what's happening in your cup. You're taking a hot piece of metal, throwing it in cold water. What does our intuition say about how the temperature of the water changes? How should that cold water change? It should go up. Yeah, if you throw something hot in cold water, the temperature will increase of the water. The temperature of the metal block will decrease. Yeah, so what's happening is that heat is being transferred from the block into the cold water, all right? So we can still use this whole first law of thermodynamics thing, all right? Heat lost by something is always gained by something else. So let's be hyper specific here. What is losing the heat? The metal is losing heat, and what's gaining that heat? It's the water, all right? So let's look back at what information is given here. We have two Q's. Think about the ways that we can calculate Q. We can use Q equals MCAT. We can use Q equals CAT. Look at the information given. I'm given the masses of both the metal and the water. Do I know the specific heats of the metal and the water? Yes, I do. And so therefore, since I also know the initial temperatures of both of them, I can also calculate those temperature changes. So what we're going to do is Q equals MCAT both sides this time, all right? Before, in these reactions we did up here, we only Q equals MCAT one of the sides to relate to Q of reaction. But in this one, we're going to Q equals MCAT both sides, and we're going to calculate what is the final temperature. So what do I mean by that? Okay, so we're going to Q equals MCAT both sides, all right? So Q of the metal is equal to mass of the metal. I'm going to just say of aluminum. Specific heat of the aluminum. Delta T of the aluminum final minus initial. So I'm just going to say final temperature of the aluminum minus initial temperature of your aluminum. All right, so that is the Q of your metal, the heat lost by your metal. And then we do the same thing for water, the mass of the water, the specific heat of the water, and then the temperature change of the water. So T final of the water minus T initial of the water. So let's look and see what pieces of information are given. Do I know the mass of the aluminum? Yes. Do I know the specific heat of aluminum? Yes. Do I know the final temperature of aluminum? No, I don't. That's what I'm trying to calculate. Do I know the initial temperature of the aluminum? Yes, that's given. Mass of the water, do I know that? Yep. Do I know the specific heat of the water? Yep. Do I know the final temperature of the water? Nope, I'm trying to calculate that. And then the last one, initial temperature of the water. Yes. So it looks like we have two variables here. Final temperature of the aluminum, final temperature of the water. But what's special about those two numbers? They should be the same number. So I can just make this a lot simpler and just say final temperature, all right? All right, so that's one variable. It's the same variable, but it just shows up on two sides of the equation. So when we look here, we know all of these numbers and we just have one variable, but it shows up on two sides of the equation. So we just have to do, a little bit of algebra to figure out what that is. So I'm gonna just go ahead and place all the numbers that we know and do some algebra to figure out what is this missing variable. So mass of your aluminum, what is it? 35 grams. Specific heat, what is it? 0.88. All right, I'm going to just drop my units. We know what they should be. Final temperature, that is what I'm solving for, minus the initial temperature of the aluminum, so this is 95 degrees Celsius, equals mass of your water, so this is what, 180 grams. Specific heat of the water, 4.184. I'm solving for final temperature of the water, and then the initial temperature of the water is 19 degrees Celsius. All right, so we just have one variable that we are solving for. So our strategy here with algebra is to get all of those variables together on one side so we can calculate what that is. So there's a lot going on here. So to prove to you that I do know how to do simple math, this is my approach. I will multiply these two numbers together and distribute them across that parentheses, right? Okay, all right, so let's do that. If you do that, you get, and do not forget that negative sign or you will be very sad. Negative 30.8, there's my variable. Plus, because it's minus a negative number, plus 2,926, all right? So we have a coefficient in front of our variable plus a constant equals, and then we're gonna do the same thing for this one. Multiply these two numbers together and then distribute it across that parentheses, right? So we get a term with your TF variable. So this first term is what? 743 TF, there's my variable, minus 14309, all right? So now my next step is put together all the TF variables, put together all the constants. So what I'm going to do is add 30.8 TF to both sides, so 30.8 TF to both sides, and then add this 14,000 number to both sides as well. Right, and so what that does is we get something that looks like 17,235 equals 783.8 TF. There we go. So now we have a constant equals our variable with that coefficient out in front. So then to isolate that variable, I mean, if you're not following along, maybe swapping out TF with an X, just change it to X and solve for X. Maybe you'll see how this algebra comes together. This is probably one of the more complex algebra equations that we've done so far. Solve for TF by dividing both sides by 783.8, 783.8, and then we get that your final temperature is equal to 22 degrees Celsius if you divide those two numbers. All right. So that was a lot of work to just calculate the final temperature of mixing this hot thing and this cold thing. It was made complicated because the final temperature showed up on both sides of the equation, so we had to do some algebra to combine them together, isolate that variable to solve for it. But before we move on, let's make sure, does that answer make sense? You start with something at 19 degrees Celsius and something else at 95 degrees Celsius. You mix them together and you end up at 22 degrees Celsius. Does that answer make sense? It does, because we want a temperature in the middle. If we would have done all of this and got like a temperature like 10 degrees Celsius, would that make sense? It would not, because how can you take something that's 95, something that's 19 degrees Celsius, and end up with something even lower than both of those. So let's make sure that our answers make sense. In this case, it does. Our final temperature is slightly elevated. Basically, we heat up that water by how much? 3 degrees Celsius by adding that small piece of aluminum. All right, so in this question, I don't know if you noticed, but we made a little bit of an assumption, right? Notice how I said here in a lot of these questions, I say this, and I've kind of been skipping over it. Assume there is no heat loss to the cup or mug, all right? The thing is that's not always the case. You know, when we think about energy transfer, if we have a hot cup of coffee in a coffee mug, will it stay that hot, toasty temperature forever? No, all right? So in the real world, there is heat loss to your mug or your coffee cup. So in this next question, we're gonna calculate, okay, well, what if you do this exact experiment? We can calculate the theoretical maximum heat transfer will result in a 22-degree final temperature. But let's say you do this in lab, but instead of reaching that theoretical maximum, 22 degrees, let's say you do this reaction and you only reach 21 degrees Celsius. What does that mean? It means that when this process happened, some of the heat went into the water from the hot piece of metal, but some of it actually went to the cup itself, all right? So this means that your cup isn't entirely efficient. The cup itself is absorbing some energy as well. So we also have to sometimes consider the heat capacity of the cup itself. That cup can absorb some energy. And I think you will discover this in the IHT lab, that not all processes perfectly transfer energy. So how we get around this is by expanding what our surroundings is. So what we have been saying before is that the heat lost by something is always gained by something else. In the previous question, we said the heat lost by the metal is gained solely by the water, but in this case, to make it more realistic, we're gonna say that the heat lost by the metal is actually gained by the water, but also the calorimeter also gains some of that heat energy as well. So we're just gonna expand what our surroundings is. So, you know, we always have to decide when given a Q, are we going to use Q equals MCAT or Q equals CAT? In this case, we know, you know, the specific heats of the metal and the water, so we're going to Q equals MCAT that again, but this time for Q calorimeter, we're actually going to use Q equals CAT. We're going to use heat capacity instead. So what this process is, heat capacity. What this process is called calibrating your calorimeter. It's a step in the IHT lab where you're going to determine how much heat capacity is inside your specific, your cup. How efficient is it? So let's write, these are like what your observations would be in lab. All right, we're going to do the same experiment. Aluminum, 35 grams, initial temperature 95 degrees Celsius. But here I'm telling you, instead of reaching that theoretical 22 degrees Celsius, the water ends up being a final temperature of 21 degrees Celsius. This is what you actually measure in the lab, all right? So we're gonna use this information and determine what is that leftover energy that had to be absorbed by the calorimeter itself. So we're going to Q equals MCAT your metal and your water, but this time we're going to figure out what is that leftover amount going into the calorimeter. So I'll write out the values that we need to use. Well, Q equals MCAT your metal, so mass of your metal, in this case it's aluminum, specific heat of your aluminum, and then delta T of your aluminum. I'm gonna just go ahead and calculate delta T's for both of these things, so I don't have to muddy up my equation. So what is this? Final minus initial. So for aluminum, it's 21 minus 95. So your aluminum lost 74 degrees Celsius. Do we agree? Yes. Okay. Your water gained what? 2 degrees Celsius. because final is 21, initial is 19. So it gained 2 degrees Celsius. So those numbers will go inside this Q equals MCAT equation. All right, so we'll do the same thing for water. So mass of your water, we know what that is, specific heat of your water, delta T of your water. But now, since we are calibrating our calorimeter, we're gonna tack on this Q cal at the end. So let's just see what happens, all right? Let's put in these numbers. So negative 35 grams, specific heat of aluminum, 0.88, delta T of your aluminum, negative 74 degrees Celsius, equals mass of your water, 180, specific heat of water, 4.184, delta T of your water, 2 degrees Celsius, plus Q cal. So I want to actually write out these numbers so you see it. So if your aluminum lost this much temperature, if I multiply all these things out, what do I get? I get that the aluminum lost 2,279 joules of energy. All right, that's multiplying those numbers together. In a perfect world, all of that energy would go to the water. But let's calculate how much energy did the water actually gain. 180 times 4 times 2 is equal to 1,506 joules. So look, we just calculated the piece of metal lost 2,000 joules of energy, but the water only gained 5,000 joules, or 1,500 joules of energy. So where is that last 500 joules? Where did it go? It went into the cup. So that's this whole idea that your calorimeter is making up for that difference of how much your piece of metal lost and how much the water gained. So we can calculate that missing piece, that missing, what is this, about 700 joules of energy went into the calorimeter itself. It gained 773 joules of energy, all right, in this process. So yeah, the calorimeter gained 700 joules of energy, but that's not quite what we want to calculate here. In the original question, we want to calculate what is the heat capacity of our calorimeter, all right? So we're going to set this equation equal to our heat capacity equation, which is right here. Q calorimeter is equal to C, that's heat capacity, so I'm going to just say C cal, times delta T. So delta T of your calorimeter is the same as your water, all right? It's the same as your water. We're going to assume that the cup changes the same temperature as the water itself. So we already know what delta T water is. This number is 2 degrees Celsius. So 700 joules of energy equals C cal, 2 degrees Celsius. So we can calculate that C cal for this experiment is about 387 joule degree Celsius. And so what we just did is calibrate our calorimeter, that we did a process, all right, a heat transfer process with a known amount of energy transfer, determined how much energy did that calorimeter gain, so we can use it for subsequent calculations. What this number means is for every degree increase the water makes inside that cup, the calorimeter itself also has to gain 387 joules. So notice that we're using heat capacity here. We're not using specific heat, and it's because the mass of the calorimeter doesn't matter. It's made of styrofoam. It doesn't have a very unique specific heat that we can calculate. So what we're gonna just do is use heat capacity and consider that whole cup heating up in that process. Right, so this is definitely a harder one of those questions, considering, hey, what if heat transfer isn't perfect? What if your cup is actually gaining some of that energy as well? All right, so let's look in some, so we did a couple questions that were very math heavy, so let's do some conceptual questions that technically shouldn't require any math at all. All right, so let's see if you understand the idea, negative Q of your system is equal to positive Q of your surroundings. Think about how the water temperature changes depending on how much reaction you're actually doing. So let's say we mix 1 liter of 1 molarity HCl. So how many moles of HCl is here? 1. This is 1 mole of HCl. And we react it with 1 mole of 1 molarity sodium hydroxide. So that means there's 1 mole of sodium hydroxide there, right? Okay, and so you mix these two things together to make 2 liters of solution. Doing that raises the temperature 6 degrees Celsius, right? So what if we did the same reaction but changed it a little bit, and let's say we reacted 1 liter of 2 molarity HCl with 1 liter of 2 molarity sodium hydroxide to produce a 2 liter solution. What is the temperature change going to be, right? So in the first question, I'm saying, oh, you mix 1 mole of acid with 1 mole of base. In the second reaction, what are we mixing? 2 moles of acid with 2 moles of base. All right? So are we generating the same amount of Q in this second one? No, we should be generating how much Q? Double, yeah, because there's double the amount of matter that's there. So if we double the amount of heat, but we're heating the same volume of liquid, what should our temperature change be? It should go up by, how much do you think? 12 degrees Celsius, yeah, because we doubled the amount of Q reaction that happened, because we're doubling the amount of reactants that are there, right? So let's do another one. Let's say dissolving 1 mole of solid to produce a 2 liter solution decreases the temperature by 4 degrees Celsius. So this is a different example. How would the temperature change if we dissolved 2 moles of solid in 2 liters of solution? So we're starting with 1 mole, dissolving it in 2 liters, we get a 4 degree temperature change. If we double the amount of solid, we are doubling Q. We're dissolving it in the same amount of solution. So what kind of temperature change should we see? A decrease by 8 degrees. Yes, 8 degrees Celsius. All right. So then this follow-up one, what if we dissolve 2 moles of solid, but this time in 1 liter of solution? 1 liter of solution. So if dissolving 2 moles in 2 liters goes down by 8 degrees, 2 moles of solid, it's the same amount of Q, but if we're dissolving it in 1 liter of liquid, is it easier or harder to heat up or cool down 1 liter of liquid? It should be easier. So how should this temperature change differ? It should go down by 16 degrees Celsius. Yep. All right? Because there's less matter there. All right? And so if we provide the same amount of energy, basically our energy goes twice as far. All right, and then finally here. So hopefully that requires no calculations at all. It's just understanding how, matter can change Q and how changing the volume of the liquid that we're trying to heat up or cool down changes your, that mass component in Q equals MCAT. All right, and the last one here. Which has the smaller calorimeter constant? A Starbucks cup or an expensive Yeti cup? Which one has the smaller calorimeter constant? So let's remember where the calorimeter constant comes from. It's the idea in this heat transfer where this hot object transfers some of that energy to the cold water, but some of it goes to the cup itself. So which cup absorbs less heat in this process? Which one allows us to do the most efficient energy transfer? The Yeti cup or the Starbucks cup? It's going to be the Yeti cup. Yeah, in that one, you're going to get the most energy transfer because you're isolating your cup away from the actual reaction and process itself. The Yeti cup is like double-walled. It's a vacuum on the inside, so you isolate that reaction from the rest of the universe, essentially. All right. Okay, so that's all conceptual stuff, and that's the hardest math calculations that we'll be doing in this chapter. So please come to office hours today and we can do more practice problems together. All right. Oh, we got one more calorimeter process to do, and that is bomb calorimetry, but this one's a lot more straightforward. So in this process, bomb calorimetry, we're not doing the reaction in a cup. We're doing it in a concealed container. This process is good for reactions that generate a lot of gases. Right? So typically when we use a bomb to determine the enthalpy change for a reaction, we will calibrate the bomb. What that means when we calibrate is we calculate what is the total heat capacity of the entire instrument. All right? So it means we calculate how much energy does it take to heat up the calorimeter by X number of degrees. This C-cal will have the unit joule or kilojoule per degree Celsius like most heat capacities. So when we're calculating the Q of our reaction, it's just like before. Negative heat lost is always gained by something else. So any energy released by our reaction is always gained by the calorimeter. Our calorimeter is not going to do Q equals MCAT. Instead, we're going to use Q equals CAT, where CAT comes from C-cal, your heat capacity of your calorimeter, which I just talked about up here, and the temperature change of your calorimeter, right? So typically you are given this total heat capacity of your calorimeter. So yeah, basically we can calculate Q of our reaction, again, if we calibrate our calorimeter and we know the temperature change of our calorimeter. So with bomb calorimetry, the calculations are actually a lot easier. So let's just do an example, all right? Okay, so we react a 22-gram sample of quinone. We burn it in a bomb calorimeter. It contains water, but the total heat capacity of the bomb is 7.8 kilojoules per degree Celsius. So after burning the quinone, the calorimeter increases from 23 degrees Celsius to 30 degrees Celsius. So I'm just going to go ahead and calculate that delta T while we're here. Right, the delta T is something like 7.13 degrees Celsius. Right, that after burning this sample, our calorimeter increased by that temperature. So we're going to use the same strategy as before, use our intuition to determine the sign of delta H of our reaction. It's going to be negative again because we're burning something, the calorimeter is heating up, meaning that the reaction released energy. It's another exothermic reaction. So something's losing energy, something's gaining energy. Let's be super specific. The reaction is losing energy, and it's being gained by your calorimeter, your bomb calorimeter. But this time, we're going to use the heat capacity of this calorimeter. We're going to say negative Q of our reaction is equal to the heat capacity of our calorimeter times delta T of our calorimeter. So let's look at this. Do we know the heat capacity of our calorimeter? Yes, it's given. Do we know the change in temperature of our calorimeter? Yes, it's given. So we'll plug in those numbers, 7.854 kilojoules per degree Celsius times the temperature change that actually happened, 7.13 degrees Celsius. So we get that our reaction lost some energy, but then our calorimeter gained 55.9 kilojoules of energy. All right, so notice, because we were given total heat capacity of the calorimeter, we don't have to do specific heats at all. Even though I gave you the volume of water that was inside that calorimeter, that value is tied up in the total heat capacity. I already calibrated it for you, so you can just go ahead and use that heat capacity C-cal that is given here. I hope at this point it looks very familiar. Negative Q reaction is equal to 55 kilojoules of energy. So this reaction released negative 55.9 kilojoules of energy. Will you find this number in textbooks? Nope. What do we have to do? Scale it to a delta H value. All right. So we got the Q of this specific reaction when burning 2.2 grams of this stuff. So let's convert it into a per mole amount, where delta H of this reaction is equal to the Q of the reaction we just calculated over the mole amount that's actually reacting. So we're going to take the gram amount of quinone and its molar mass to convert it into a mole amount. All right? So this value will equal negative 55.9 kilojoules over the 2.2 grams of quinone. Use molar mass to convert it, so 108.1 grams is 1 mole. This number on the bottom is something like, I didn't actually write it, 2.2 divided by 108.1. So we actually only reacted 0.0204 moles of stuff. So when we scale this into a per mole amount, we get that burning a mole's worth of quinone will release negative 27,000 kilojoules of energy. Right? So the idea of bomb calorimetry, burning these substances to determine how much energy is released, it's basically where our nutritional calories come from. That's how they determine where nutritional calories are. They literally take like Cheerios and put them in there, burn them to see how much energy is released, convert it into the unit calorie to figure out how much energy, does these food sources supply to our bodies. So this is called bomb calorimetry. We're burning things, we're combusting it. What do they say when you like work out a lot? What are you doing to your calories when you work out a lot? You burn your calories? Yeah, so there's like a reason that we say burning calories. It's really no different than a combustion reaction. Okay, all right, so that is calorimetry. Two types, coffee cup, bomb. Bomb is a lot more straightforward, as long as we're given that total heat capacity there. But the process is the same. We'll use first law of thermodynamics to calculate Q, scale it to a delta H of reaction by dividing by the mole amount that you're actually reacting. All right, so we got about 40 more minutes, so let's do the last two parts of this chapter. They will be a lot more tame than what we just covered. All right, and so these next two sections are the last two ways we will calculate enthalpies of reactions. Calorimetry was the way we calculate enthalpy experimentally. So like going into lab and like doing stuff, we can calculate delta H, but we can also use book data to determine the delta H of a reaction. We're going to be definitely utilizing Hess's law here. So the first way that we can calculate enthalpy values using book values is by using standard enthalpies of formation. So this has a symbol, delta H, with an F and a little 0 there. All right? So these, you can look up standard enthalpies of formation for any substance. Right? So that's what I mean by this is a book value. So what is this enthalpy of formation value? It is the amount of energy to form 1 mole of a substance from its elements in their most stable state. All right? So these are table values where you can take any substance, you can find its delta H of formation, but what that number represents is forming 1 mole of that substance from its elements in its most stable state. So let's look at an example. What do I mean by elements in their most stable state? Here are all examples. Oxygen in its most stable state, how you'll find it on Earth, is O2 gas, or nitrogen gas. Or if we're talking about carbon, it's carbon solid, but specifically graphite. Graphite is actually more stable than diamond. Zinc solid, iron solid, those things, all right? So you know the saying, what do they say about diamonds? Not that diamonds are a girl's best friends. What's the other one? Diamonds are forever. So technically, if carbon is more stable than diamond, are diamonds really forever? No, graphite is actually forever. So anyway, so let's write the standard enthalpy of formation for methane. This is the strategy. If I asked you what is the standard of formation for methane, what you're going to do is take methane, 1 mole of methane, and make it the product. Then you're going to look at all the elements present. You see, oh, there is 1 mole of carbon. So you're going to write 1 mole of carbon, but carbon in its most stable state. So that is going to specifically be carbon solid graphite, not diamond, right? To make it balanced. So 1 carbon, because there's 1 carbon in that methane. Next, we have hydrogen. Hydrogen in its most stable state is H2 gas, right? But is this balanced? Nope. This is where we got to add some coefficients, so you're just going to simply put a 2 in front of that hydrogen gas. Right? So what we are writing here are the elements present in that compound in its most stable state, balance it with its coefficients so you make exactly 1 mole of the product. So if you look in a textbook or something, you can find the delta H of formation for this value. I'm not quite sure what it is, not sure. You could look it up. I'm just going to make up a number like negative, like 256 kilojoules per mole or something. You'll find that number, but what that number represents is the enthalpy related to this reaction right here. Right? I actually don't know what the delta H is, but you could look it up in a book. All right, so this is like what you would look up in a textbook. All right. If you go to your appendix in your textbook, you'll find a bunch of delta H of formation values, tons of different substances, but you need to recognize that these values, these delta H values represent a reaction. So if I ask you, what is the delta H of formation of ethanol, you'll know, oh yeah, I just go to the book, it's negative 277.7. But what does that energy value mean? It has a balanced chemical reaction associated with it. So let's go ahead and write the balanced chemical equation that represents this formation value. So our strategy is you take ethanol, so here's the formula, and we're gonna make exactly 1 mole of this substance, all right? And then we want to form it from its elements in its most stable state. So we got carbon again, carbon, solid, graphite. But how many carbons should I have? 2, very good. So next, we did carbon, let's do hydrogen next. So it's H2 again, H2 gas. But how many hydrogen molecules should I have? 6, yeah, be careful because there's a total of 6 hydrogens here. There's 5 and then 1 tacked on the end. So there's actually 6 H's here, so you need 3 of them, all right? And then the last one is an oxygen. So oxygen in its most stable state is O2 gas, all right? But how many oxygens do we want on the reactant side? Just 1, so our coefficient we're gonna use is a half. So back in chapter, 3 or whatever, when we were balancing, we said, oh, always, multiply by, a integer to get rid of the fraction, but the fraction is absolutely okay here because the definition of a formation value is forming exactly 1 mole of your product. So if we multiplied by 2, are we still making only 1 mole of stuff? No. So we actually want to keep that fraction. That fraction is okay for formation reactions. And again, it's because we're deliberately trying to make 1 mole of that product, all right? Okay, so let's do some more here. All right, so let's also write the formations for these different substances. So our strategy here is you're going to take your thing, make it a product, and form it from its elements in its most stable state. So you're going to go through all of them. So first we have sodium. Sodium in its most stable state, it's a metal, so it's most likely going to be a solid. Yep. So you need 2 of them. What else? We got carbon again. So carbon, solid, graphite, and then what's last? Oxygen. So we have O2 gas, but how many of them? What should my coefficient be? 3 halves. Yeah, because we need 3 of them, right? So, you can look up in a textbook what this formation value is, get that value. That value represents this equation. All right, let's do another one. Silicon, the silicon bromide thing, SiH3Br. So we go through each thing. Silicon is a semi-metal. It's going to be a solid. All right, there's only a handful of gases on this periodic table and I think 2 liquids. Next we have hydrogen. This is H2 gas again. What's our coefficient in front of there? 3 halves. And then finally bromine. What is bromine in its most stable state? Liquid, but what's the formula? Is it just Br? Nope, it's one of our 7 diatomics, so it's actually Br2, and it's a liquid, yes. What's the coefficient there? 1/2. Right, so do be careful about that. Bromine, understand our common diatomics and common states of things. Most metals are actually all of the metals are solids, except mercury. There's a handful of gases, yeah, and then our 7 diatomics. All right, let's write O2. So what is the strategy? O2 is the product. Ask yourself, what is its elements in its most stable state? O2, yeah, interesting. Huh, interesting, yeah. So if you look up O2, the formation value for O2, what number are you going to come across? How much energy does it take you to go from O2 gas to O2 gas? 0, yeah. So what we find here is that any element that's already in its most stable state, if that's involved in a chemical reaction, that formation value for that thing is actually 0. Right? So you probably won't find formation values for elements in their most stable state, and the reason is because it's 0, because if we apply our definition, it does not take any energy to do this process. All right, so what are we going to do with these numbers? It allows us, since these are all table values, it allows us to take a full chemical equation and determine what is the enthalpy of this entire reaction. So what we can do is utilize Hess's law. If I know the formation values of all of my products and all of my reactants, I can basically just say, oh, if I form all the reactants in all of my products, I can calculate the overall energy change for this reaction. So here is the general equation of what we want to do. If we have our given formation values, to calculate the delta H of the reaction, you're going to sum up all of your formation values for your products, and you're going to subtract all of the formation values of your reactants, right? So these values are here, they're given. So what I like to do is take inventory. If this is my balanced chemical reaction, I can see, oh, methane, negative 74.8 kilojoules per mole. CO2, negative 393.5 kilojoules per mole. Water, negative 285.8 kilojoules per mole. But how many water molecules are there? 2 of them, so we need to multiply this number by 2. All right. But where's oxygen? I wasn't given oxygen, so I can't do this problem, right? What is the formation value for oxygen? It's 0, so you do need to know that. You need to know that, all right? And so now I have all of those formation values. So what I'm going to do is just sum up each side, all right, with those values given. So what we see is on the reactant side, the total formation value is negative 74.8, and on the product side, it's something like negative 965.1. All right, these are my products. Here are my reactants. So when you calculate the delta H of your reaction, you want to do products minus reactants when dealing with formation values, all right? The reason I do it this way is because you're going to find a lot of formation values with negative numbers, and I hate doing minus negative numbers, and like there's going to be a lot of negative signs floating around, and so by doing it this way, calculating both of them separately and bringing them together, you're least likely to make a negative sign mistake. So what we have here is our products are contributing negative 965.1 kilojoules of energy minus negative 74.8. See what I mean by a minus a negative, all right? So do be careful about that. And so what we get is that the overall energy change for this reaction is negative 890 kilojoules per mole, right? What else did I wanted to say about this? Oh, notice this reaction, I have water as a liquid, but I have 2 different formation values of water here. So do make sure that you use the correct one, because we see that the numbers are a little bit different. So if I'm talking about a liquid, make sure to use the liquid value, right? If this was a gas, you would use the gas value, all right? And the total enthalpy change for this reaction would be slightly different depending on what states of matter that we have here. All right, yeah, so yeah, pay attention to states. So let's do one more here. Okay, this one's a little bit different. I give you some values, but not all of them. And this one, I'm asking you calculate the formation value for one of the substances. This time, I'm giving you the delta H of the reaction, right? So I don't know. I'm trying to figure out what is the formation of that substance. and I give you some formation values down here, all right? So I like to associate, write the formation values under the substances. I like to organize my thoughts. So HF is negative 272.6. C2H6 is negative 84. I don't know what C2H5F is, so I'm just going to actually call that X, because that's what I'm going to be solving for. And then what is F2? I didn't give you that. Yes, it's 0. Yeah, so don't think, oh, you didn't give me enough information. No, F2 is an element already in its most stable state, so it's 0. All right, so we're going to do the same thing, right? Sum up the formation values of all the reactants, all of the products, and then recognize that the total enthalpy of the reaction is always products minus reactants. So my reactants total is negative 84, but then my reactants is X minus 272.6. Those are my products. So here I am, I'm going to solve for X. So remember, here's my delta H of my reaction is equal to negative 469.3 kilojoules equals products minus reactants. So X minus 272.6. Thankfully, everything's a 1-to-1 ratio here, so that's nice. Minus negative 84. All right? So putting that math together, I think you get X is, so if you solve for X here, you get that X is equal to negative 280.7 kilojoules per mole. So this value is your delta H of formation for that missing piece, C2H5F. All right, so this question, very similar to the previous one. It's just I gave you a different variable to solve for. All right, so that's how we can use enthalpy values. It's as long as I give you formation values, you can use products minus reactants to calculate the total enthalpy of your reaction. All right, so we got 15 minutes left, so we will go over the last way we will calculate enthalpies of reaction, and I think this is the most fun way, personally the most fun way to calculate delta H of reactions, right? When reactions happen, maybe something we've neglected to think about is when we have reactants and we make products, what we're doing is we're breaking chemical bonds and we're forming new chemical bonds in our products. So when we think about this, breaking bonds always requires energy. We talked about this before, all right? Breaking a bond always requires energy. It's a positive amount of energy needed. Making bonds always releases energy. So if I give you bond enthalpies, or like how strong a bond is in, if I give you like a chemical reaction and I tell you, okay, like a hydrogen-hydrogen bond has this amount of energy, we can, again, use Hess's law to calculate what is the overall energy change of a reaction by inventorying what bonds do we have to break and what bonds do we have to make. So in this last process, we're going to break our bonds and make our bonds to figure out what is the overall energy change for a reaction. So without doing any calculations, look at this definition. Tell me the sign of delta H for these reactions. This first one. We're taking two things and we're making what? One thing. So what are we doing? Are we breaking bonds or forming bonds? Forming a bond. So what is the sign of delta H here? Negative, because we're forming a bond. What about the next one? We're taking two fluorines and we're making one F2 molecule. So what are we doing? Breaking or forming? Forming, so delta H is negative again. Okay, great. Okay, now we're taking magnesium cations, chloride anions. We're bringing them together. So what is the sign of delta H? Negative again. Yes, we're forming bonds. And then the last one, we have HBr, and then we're forming a hydrogen atom and a bromine atom. This is breaking, so this is delta H is positive. Breaking bonds requires energy, making bonds releases energy, all right? So what about bond energies? What we know about bonds and these energies is if delta H for a bond is large, what that means is it takes a lot of energy to break that bond, so that bond is strong. Or we can say, oh, if delta H is really large, it takes a lot of energy to break, that bond is short. So a large bond enthalpy means two things. That bond is strong and it's short. Here are some examples of bond enthalpies. Here's an example. Here's a carbon-carbon single bond, 350 kilojoules per mole. But if you want to break a carbon-carbon double bond, look, is stronger and it's shorter. And we see that the bond enthalpy required to break it is much, much higher, all right? So we see that manifest itself here. So how is this helpful for us? Well, if I give you a chemical reaction, and you can kind of play like Legos. If you break all the bonds that you need to then form all the bonds that you need, figure out the energy required to do that, add up all those steps, there you have your delta H of your reaction. So here's an example. Let's say we start with CH4 and Cl. And here are our products, CH3 with a chlorine attached and HCl. So in your mind, if you think about like if you were playing with Legos, how would you turn this picture into this picture? We're just kind of like taking a green atom and swapping it with a white atom, right? But really think about how do you do that? Like if you're playing with Legos, you can't just say, oh, swap those two pieces. What we actually have to do at like a step-by-step level is break this bond, break that bond, because then now we have the white and the green atom loose, then swap them, all right? So what we're gonna do is break these bonds, so then now they're loose, and then you can make new bonds. We're gonna make a bond there, and we're gonna make a bond there, and make these bonds on this side, right? So when using bond enthalpies, what we're gonna do is delta H for the reaction is all the bonds you break minus all of the bonds you make, right? Because breaking bonds requires energy, making bonds releases energy. So let's use these structure drawings to help us and figure out what is the delta H for this reaction. We're going to take CH4 and a chlorine molecule. We're going to break these two bonds, and then we're going to actually form these two bonds, right? So I like to take inventory. Determine what is the energy of all the bonds you break. So we're breaking a carbon-hydrogen bond. And what else are we breaking? What kind of bond are we breaking? Cl-Cl. And looky over here, I give you these values. So the energy to break a CH bond is 413, and then a Cl-Cl is 242. So it costs me how much? 655 kilojoules to break those two bonds. Now that they're broken, I can swap their places. But in doing that, I form new bonds. So let's look at the new bonds that I form. Now, what kind of bond is this? This is a carbon-chlorine bond, so I'm going to make this bond. And what is the other bond that I make? What's this bond right here? This is a chlorine-hydrogen bond, right? So then we look at our table over here. Carbon-chlorine is what? 328. Chlorine, hydrogen, that's hydrogen chlorine, but same thing, 431, right? So the energy that came from when we made these bonds, these new bonds, is 759 kilojoules, right? So we break, we make, so when we calculate delta H, it's always break minus make. You can think, oh, the energy to break bonds, this is a positive number. When we make bonds, we get this energy back. So that's why it's break minus make. So delta H of this reaction is equal to 655 minus 759. And we see that the delta H of this reaction is, negative 104 kilojoules, right? This is an exothermic process. Delta H is negative. Energy should be released during the course of this process. Why is this number negative? Why is this number negative? Is it because the bonds in the reactants are stronger or the bonds in the products are stronger? It's because the bonds in the products are stronger. Notice that the strength of the bonds that we make are stronger, so when we subtract them, we get a lot more energy back, all right? So let's do one more here. This is the last slide. So let's do the same thing. use bond enthalpies to calculate what is the total energy change for this reaction. So what is this? This is a combustion reaction. We are combusting ethane, C2H6. So in this question, so in the one we did up here, notice how we only broke the bare minimum of pieces to make the products. We only broke 2 bonds and made 2 bonds. But what we could do is break everything and make everything if we wanted to. And that's what we're going to do in this last example, right? We're going to break everything and make everything. So we're going to do the break minus make again. So we're going to inventory all of the bonds that we have to break in our reactants and all of the bonds we have to make in our products. But we got to be really careful, all right? Because what are we burning? We're burning 2 ethane molecules. So we're burning 2 of these, all right? So if there is 1 carbon-carbon bond here present, how many total carbon-carbon bonds are present in 2 ethanes? 2 of them, yeah. So we actually have to break 2 carbon-carbon bonds. And now tell me, how many carbon-hydrogen bonds are there? 1, 2, 3, 4, 5, 6. So how many total carbon-hydrogen bonds do we have to break? 12. Very good. All right. What else do we have to break? Is that the only thing we have to break? Nope. We got to break these oxygen molecules. All right. So 1 oxygen molecule has a oxygen-oxygen double bond, but how many total do we have to break? 7. We got to break 7 of them. Right. So we can look up the bond enthalpies for those different bonds down here. So carbon-carbon is 347, 348, but we're going to multiply that by 2. There's 12 carbon hydrogens, so that is times 4, 13. And then there's 7 oxygen-oxygen double bonds, so make sure you use the double bond one. So 7 times 495. All right, we're going to add up all those numbers. I'm going to do it at the end. Okay, so we broke everything on our reactant side. So now what do? We got to make everything on the product side. So same deal. Okay, so let's look at this CO2 molecule. Notice that there's a CO double bond, but how many total CO double bonds are there? 2, but then how many CO molecules are there? 4. So how many CO double bonds do we make? 8. Do we see how we got the 8? Okay. So that has a number. We'll multiply that number by 8. And then what else are we making? Oxygen, hydrogen. So tell me, I'm not going to help you this time. How many total oxygen hydrogens do we make? 12. Very good. Very good. Because each water has 2 oxygen hydrogens, and there's 6 waters. So let's take those appropriate numbers. CO is 799. Oxygen, hydrogen is 463. So let's add up all of these numbers. So all the bonds we break is something like 9,107 kilojoules, I think. Let's super check that number. It doesn't seem right. Is it right? Oh, yeah, it is. Okay, it's about 9,000 kilojoules. That is what we have to break. But then what do we get back? What do we make? We make 11,948 kilojoules worth of bonds. So when we calculate the enthalpy of this reaction, what do we do? How do we do those numbers? We do break minus make. All right, so we broke 9,000 kilojoules worth of bonds, but we get back 11,000 kilojoules worth of bond energy. So this reaction has a total enthalpy of 2,800 kilojoules, right? That the bonds that we make are so much stronger. So yes, we know this reaction is exothermic, but why? It's not because we broke bonds. This reaction is exothermic because we formed products that have much stronger bond strength. All right, the minus the make part is a very large number that we subtract, and that's what makes this reaction exothermic. All right, so that's it for chapter 5. So that means that chapter 5 homework is due on Sunday. Have a great weekend. Yep.